Now that we know that quadratic sequences are sequences that have a common second difference, we have to take a look at their general properties so that we can solve problems using the properties. Now, all quadratic sequences have the following general term. So we can use this general term to represent all quadratic sequences. It's actually a familiar term because we've seen it in quadratic equations and quadratic functions. So the term is Tn can always be represented for quadratic functions as an squared plus bn plus c. Then it must be the condition that a cannot be equal to 0, because if a is 0, this whole term goes away, and if you can take a look there, we will have something linear because the highest exponent would be 1. So therefore a cannot be 0 in all quadratic sequences. Secondly, we are going to utilize our knowledge of functions and how to get function values to analyze what happens for the terms of such a sequence. Now we are going to conventionally start from 0, even though in our sequences we don't deal with term number 0. So let's take a look at what happens if n is 0, n is 1, n is 2, and n is 4. That will be enough for us to get all the properties. So firstly, when n is 0 in this sequence here, we will have only c, because this term will go away and this term will go away. So only c will be left. Secondly, when n is 1, then this is 1, so we just have a. This is also 1, so we have b. Then c is c, so we will only have a plus b plus c. So you can continue checking and doing all of them, but you will find that for term number 2, we will have 4a plus 2b plus c, so it can be represented in this way. And then we have this for term number 3 and this here for term number 4. You can always double check and make sure that everything is in order. We are trying to save time. So now we are going to take a look at the first differences. Now remember that this is the most general case that we are dealing with. Therefore, what we speak of will always work for quadratic sequences. Now, when we take term number 1 and subtract term number 0, we get a plus b because the c's cancel out. Then, when we look at term number 2 minus term number 1, we get 3a plus b. When we look at term number 3 minus term number 2, we get 5a plus b. And then when we look at term number 4 minus term number 3, we get 7a plus b. Now we go a step further and go to the second differences, because we know if it's quadratic, the second differences will be equal. But take a look at how special that equality is. We find that when we take 3a plus b, subtract a plus b, we get 2a. We find that when we take 5a plus b, subtract 3a plus b, we get 2a. When it's 7a plus b, subtract 5a plus b, we get 2a. So all the second differences are actually twice the number of a. So therefore, when we do have the second difference from the one that we saw, for example, in the previous example was 6. So when we get that, we can realize that, wait a minute, we can use it to find the value of a. So 2a is equal to the second difference. So that will be an equality that we use to find a. And finally, we just have to note that in mathematics, when we have 3 unknowns, namely here a, b, and c, we need a minimum of 3 equations to be able to solve for them successfully. So in this case, we have already said, for the case of a, we have the equation 2a equals to the second difference, so we can use that equation. The second equation that we are going to need comes from here. Since we've already mentioned that c, or term number 0, is not in our analysis of sequences, so therefore this difference will not be there, so we will use this difference here, and then we will use this here as the equality for term number 1.